you get tensile residual stress. Never happen. Okay. Yeah, never happen. Okay. So what does short pinning actually mean? Okay. So if we have a workpiece over here, okay, if we have a workpiece over here, and this surface over here that you see, okay, this surface over here has gone through mechanical and thermal loading. Right? Yeah, make it going through thermal and mechanical loading. So in short pinning, what it does, this is a particle traveling at high speed, and it will hit the surface in this direction and bounce back. Sometimes it can bounce away, sometimes it can disperse. Okay. Before you do short pinning, okay, for example, before short pinning, right? Surface is usually what? Shiny, right? For example, for this case. After short pinning, the sort of surface we get is very unique. Okay, what you see after short pinning is you see this sort of surface. The surface is not flat. Sorry, the surface is not flat, but the surface tend to be what? Dull, not shining at all. Okay, so we call this dimple formation. Okay. I'm not saying that the surface roughness is no good, but it's just not shining. Okay, it can be very smooth, but it's not meant to reflect light very well. Okay. Now the next question we tend to ask ourselves, okay, why short pinning? Okay, why short pinning always induced compressive residual stresses? Okay, we tend to ask ourselves that question. Whenever you want to remove tensile residual stress, you always go through what? Short pinning. Now, another important thing I like to tell you, okay, the residual stress, important if you can put somewhere down here, okay. Okay, so the residual stresses are one of the reason for part distortion. Okay, when you see a part, when you're machining a part, okay, and then when you relieve the clamp, the part tend to spring up. This is because of what? Residual stresses. Are we clear? So in residual stress, there's no force applying to it. It is a stress that's locked in into your material due to what? Mechanical and thermal loading. Okay. Now the question now deems to us is then why, okay, short pinning always induce compressive residual stress? What is going on? Okay. So the reason is not difficult. Why is it always under compression and it's not tension? So part of it is in short pinning. Okay, the plastic strain induced is very small. Okay, I've measured them. Okay, the plastic strain induced due to short pinning is usually less than 0.005 plastic strain. Okay, now if we draw our stress strain curve, okay, so this is our plastic strain. This is our plastic stress. Okay, if we have a material, okay, this is the original geometry. And then when we bend it, after bending, this region over here, right? This region over here, we're going through a stress strain curve looking like this. Okay, and it stops here. Okay. So over here, this is the amount of energy okay, so this is the amount of energy input into the material. Okay. Now, if we look at conservation of energy, right, which means energy in will be equal to what? Energy out. So to bend the material, what we do is we put in what? Mechanical energy. And the output will be 10%, this is just a guess. Okay, 10% sound energy, 90% heat energy. When we bend, is when we start to do mechanical loading. Unfortunately, conservation of energy, it will evolve as what? Heat. Don't believe me? You take a spoon and you start bending, what happened to the corner? It becomes hot. Yes or no? Or you'll use chopstick like me. You'll use spoon, right? Keep on bending. Okay, you will have it. So if you look at over here, due to bending, right, you can see that you have a lot of energy. Okay, so over here, this is strain after what? Bending. Now, in short pinning, this is the strain induced after due to what? Short pinning. And you know, energy in is energy out, right? The heat energy evolved from short pinning is very what? Small. And for this reason and this reason alone, that's why short pinning you get what? Compressive what? Residual stress. Okay, so in short pinning, the mechanical input energy is very much smaller than bending. Okay, so therefore, lower heat energy will be evolved in short pinning okay. This will result in always compressive residual stresses. Okay. Uh, in Japan, Honda has been doing this since the 90s. Okay. We all know that long-lasting cars are the Hondas and Toyotas, yes or no? Right. But in the 90s, or even earlier, maybe in the 80s, okay, what they did, crazy Japanese, okay, if you look at this particle over here, it's either made of sand or steel. Yes or no? Right? You have these particles, can be steel balls, or it can be sand. The Japanese use ice. Smart people. When they use ice, the benefit is what? You don't need to like collect the sand, or you don't need to have a container for the what? For the steel balls. Yes or no? You just blast and then get compressive residual stress. The waste product is what? Water. Okay. And sometimes some of this sand will get stuck into the material. For aerospace application, is really, really bad. Because sometimes when you machine the blade, you will put a coating on top. But inside have what? Then crazy Japanese, yes or no? Use ice. If the ice gets stuck, what will happen? It will melt. Okay, that's why their car lasts so long. Okay, but now, okay, I don't know, do they still use that? The problem is making small ice, particle ice also require what? Energy. Okay, maybe now they go back to particles. Okay, but crazy. Now, residual stresses. Okay, should be controlled when the component is under cyclic loading